In this video, we're going to be discussing our Logger Pro work that we did in class. So right up here on the screen is some student work. They fired a basketball, went up and down, and that's the start of your lesson. But the important thing I want to focus on today is the graph that you're going to be getting from your Logger Pro video. The two graphs that you're getting are describing the ball's motion, the basketball's motion on the x-axis and on the y-axis. So what does that mean? That just means that the red dots are representative of how the ball was traveling horizontally, meaning how the ball was traveling sideways. The y dots are representative of how the ball was traveling on the vertical axis, meaning how the ball was going up and going down, because this is projectile motion. Two things are happening at the same time. The ball is going sideways and it's going up, and then it continues to go sideways as it comes down. So in the video, you can see that the ball that's being fired is traveling in a projectile path, a parabolic path. And what I want to focus on for a couple of minutes is the equation that we get from our graphs. Because in math class, we're constantly reminded of the y equals mx plus b equation, which is your linear equation, an equation that describes a linear graph. And your quadratic equation, which is ax squared plus bx plus c equals 0. And that quadratic equation describes a parabolic path. And you're going to run into this parabolic path quite often in physics, especially in projectile motion. So I want to take a couple of minutes and just look at those two equations on the board. So when I was taking math, I had a wonderful math teacher, just like you guys. In math class, we were taught that the linear equation is y equals mx plus b, which is very useful. Now, what you're going to find out in physics class that slope is a very important concept. It's going to come up again and again, because all the graphing that we've done, all the analysis we've done using graphs, x-axis, y-axis, time is being measured on the x-axis, displacement is being measured on the y-axis, the slope, the area underneath the curve, all that we've done keeps coming back to these equations and these concepts that were introduced to us in math class. For the Logger Pro video analysis activity, I want you to think about that equation, the linear equation that was taught to you in math class. However, when you look at the Logger Pro graph, when you look at the work done on the video analysis lesson, you're going to notice that the equation is x equals mt plus b. X equals mt plus b. So I want you to take a look at your video also that you analyzed in Logger Pro. The takeaways from now are the time concept. You see, in physics, we work with something called a parametric equation. A parametric equation, simply put, is an equation that tells you how an object is moving and where can it be found at a particular time interval. Where can it be found on the x-axis or where can it be found on the y-axis at a particular time interval. So that's basically what a parametric equation is. And these are all parametric equations, these graphing activities that we're doing and these ideas that we're bringing into physics class talk about where can we find a particular object at a particular time interval. So that's one of the takeaways. I want you to look at your equation and I want you to realize that there is a time interval that is being placed in this equation, because Logger Pro is helping us figure out where the object is located while it moves sideways. And sideways, remember, is horizontal motion or motion on the x-axis. So the time is telling us where the object is located at a particular time interval. The slope is constant. You're noticing that the slope idea, the m is referring to the slope, and that's something you've done a lot in math class. You're going to notice the slope is not going to change. They're telling you right here the slope is 2.368. For me, it comes out to be 2.368. Well, that's useful information because the slope is telling me, for the red dots, it's telling me how the ball is moving to the right at a particular time interval, how it's moving sideways, horizontally. So that slope is telling me how many meters it covers sideways in a particular second. And in this case, the slope comes out to be 2.368. So that tells me the ball is moving 2.368 meters per second sideways. So that's the horizontal velocity of the ball. So the slope is very useful. The slope is telling you that the ball is traveling 2.368 meters per second. So I want you to take a look at your particular graph, and I want you to focus on what the y-intercept is telling you. Now remember, for us, the y-intercept, anything that's being plotted on the y-axis, is displacement. On the x-axis, time. The red dots are representing displacement, horizontal displacement. So how the ball is moving sideways. So keep that in mind. We're going to have a discussion about what the y-intercept means in class. So think about that. The y-intercept is telling you it's on the y-axis, but remember the y-axis in this case, you're plotting displacement, horizontal displacement. So you'll have to keep these ideas all side by side. Don't let it confuse you too much. So I want to jump to the parabolic path. Remember the blue dots are representative of how the ball was traveling vertically, or what we call on the y-axis of your xy coordinate system. So how the ball went up and how it came down. So the displacement in the y, of vertical, is plotted here, again, on the y-axis. Time is on the x-axis. So you're going to notice the slope is not consistent. And the reason why that's the case, the slope is changing, is because when the ball is traveling up or down, it's not traveling at a constant velocity. When the ball is traveling sideways, like the red dots are showing you, it is traveling at a constant velocity because air resistance, there isn't enough time for air resistance to really impact your speed. However, if you gave it enough time, or if the ball was traveling fast enough and you videoed this, made a video of 2, 3, 4 minutes, then you'll start noticing air resistance is going to impact your horizontal velocity. But in our case, it doesn't, because the ball was in the air for a very short time period. However, in the y direction, you notice when the ball goes up and comes down, it doesn't travel at a constant speed because the slope is telling you it's not traveling at a constant speed because the slope is changing. The slope is decreasing for the first part and then increasing for the second part. That's telling you something. That's telling you something very important. It's telling you that the ball's velocity is decreasing as it goes up. And the reason for that is because everything around us is constantly being pulled down to the center of the planet. Everything around us is constantly feeling an acceleration of gravity downwards. So when the ball goes up, it's being accelerated downwards. So it's slowing down when it goes up. And you notice the slope is decreasing. And then when the ball starts coming back down, the ball speeds up. Gravity now accelerates the ball downwards. So you notice the slope is going to increase. The equation that you see on your end is y equals at squared plus bt plus c. And I'm also going to put this up here. Y equals at squared plus bt plus c. Now that's your quadratic equation. Now in math class, how I remember it, my math teacher taught me the quadratic equation. He said it's ax squared plus bx plus c, and set it equal to 0. It's still the same thing. In this case, time is taking the place of x. Because once again, it's a parametric equation. It's telling you where will the ball be located vertically or on the y-axis at a particular time interval. And because the ball is changing its speed, you can't use a linear equation because it's not covering the same distance in the same time interval. It's covering less distance as time goes by when the ball is going up, and it's covering more distance as time goes by when the ball is coming down. So you have to use a quadratic equation that describes a parabolic path. And this is an important equation to keep in mind because the idea how it connects with graphs is very interesting, because this equation is telling you a couple of things, at squared plus bt plus c. And this equation looks very familiar to the equation we derived in class. We derived an equation in class that we said your displacement, d final, equals your initial displacement plus your initial velocity times time plus 1/2 at squared. So d stands for displacement. Now you can use xi and xf over here if you're looking at displacement, horizontal displacement, or you could use yi and yf here if you're talking about a vertical displacement. But just to keep things simple, you can use a d also. Nevertheless, this equation that we derived, and we derived this equation in class by starting off with a simple definition of average velocity and a simple definition of acceleration. This equation goes hand in hand with the quadratic equation that we've determined from logger pro. Why? Because this part, 1/2 at squared, matches up with this. The VIT matches up with this component. The DI matches up with this. So I'm going to rearrange this. I'm going to rewrite it so it matches up directly with the quadratic equation that I have above. So this is 1/2 at squared VIT plus DI. There we go. Your quadratic equation that you're seeing up here says y equals at squared plus bt plus c. And you're pulling up your logger pro on your own laptops too. A is -5. B is 19. C is -15. This is telling you some valuable information because C represents your initial displacement. Where was the ball initially? B represents your initial velocity. What was the ball's initial velocity? How fast was it going initially? For it to go up, you had to throw it up. And for it to travel up, it must have had a velocity, an initial velocity greater than 0. Otherwise, it wouldn't have gone up. So that tells you the ball's initial velocity. And here is the most interesting part for me. This says at squared. And on your logger pro, it says a is 5. Well, a is representing this part of the equation, 1/2 a. The t is representing the t part, but the 1/2 a is being represented by the capital A in your logger pro quadratic equation. What does that tell you? Well, gravity, if gravity is 9.8 meters per second squared, if gravity accelerates everything at 9.8 meters per second squared, let's round it up to 10 for just to simplify things. If this is 10, 1/2 10 equals 5. And that is the exact same number you're getting in your quadratic equation on logger pro for A. If you go back to your quadratic equation in logger pro, A is -5, 5.3. So this is telling you that, listen, wherever you're executing this experiment, A is -5. So if you come back here and say, hey, look, if A is -5, and if A represents 1/2 A, 1/2 small a, if capital A represents 1/2 small a, and if A is -5, then small a is -10. And that's the acceleration of gravity. So you see how these ideas that were introduced to us in math class and then reinforced in the beginning of our school year in physics class about graphing, about displacement being plotted on the y-axis, time being plotted on the x-axis, the slope being the velocity, the area underneath the curve of a velocity time graph. If you have a displacement time graph, the slope is going to give you information about the velocity. However, if you plot velocity on the y-axis and time on the x-axis, the slope will give you what the acceleration is. And the area underneath that curve will give you the displacement. All these ideas that we've been talking about are coming together with the help of the video analysis that was done on this basketball. So a simple idea, a basketball being shot, and then analyzing that motion on the x-axis horizontally and vertically gives you these two equations, this linear equation and quadratic equation that reminds us of our 8th grade math, our 9th grade math, our 10th grade math. And it combines these ideas, and these ideas, when you mix them in with the physics concepts, again, what we're talking about, they tell you a lot about where the object is located, what was the ball's initial velocity, what's the ball's acceleration at particular time intervals. So these are parametric equations that we're using in our physics class, and we're combining graphical analysis with these concepts in physics about acceleration, velocity, and you're deriving these equations. You don't ever have to memorize these equations. No one should memorize any equation. If anybody tells you to just pick up an equation from a textbook and just put in numbers and just spew out an answer, it's pointless because you don't know what that answer is what it means. And in physics class, that's what I care about. I'm caring about what it means to you. So we're going to be drawing these parallels more often in class, but I did want to take a couple of minutes and review this idea on the lesson that we did on logger pro. And we're going to do this more often. We're going to take our iPads and we're going to analyze different types of motion so we can understand what the acceleration is, what the initial velocity is, what's the final velocity at that particular time. The next video that I'm going to show after this one is going to be on projectile motion. So hopefully you'll find that one useful too.